Assalamu alaikum Ibrahim. So this is going to be the chemistry class for today, and we're going to be solving the revision sheet as well as going through all the topics one by one, just to give you a quick summary of whatever you need to know. And inshallah, tomorrow the exam will go good. So the first chapter is the particle nature of matter. So what is matter, Ibrahim? Matter is everything that we can see, touch, feel. It's Matter is whatever takes up mass, basically, right? For example, the chair that you are sitting on, the bed that you sleep in, the floor that you walk, the walls that you live in, the table that you use, your laptop, your mirror, your cabinet, your pen, even your body, whatever has mass and takes up space, that is what we call matter. Okay. Now, what is matter made up of, Ibrahim? Matter is made up of tiny fundamental particles that we call atoms, and you already know this. All matter is made up of tiny particles called atoms. They are tiny fundamental particles and they are called atoms. Okay, so everything is made up of atoms. Your table, your body, your pen, your laptop, your carpet, your curtains, right? Your car, trees, everything is made up of atoms. Now, matter can be in different states, and you already know this as well, the three states of matter: solid, liquid, gas. An example of a solid thing is your table, right? Anything that's solid, like ice is also solid, metal is also solid, um, your pen is also solid. What about liquid? Obviously, we know that liquids, examples of liquids are water, oil, juice, milk. All of these are liquids. And gases: oxygen, radon, argon, nitrogen, carbon dioxide, carbon monoxide, sulfur dioxide, nitrogen dioxide. All of these are gases, Ibrahim. The air that we breathe is also a gas. Okay? The air in the Earth's atmosphere is also a gas. So these are the states of matter. Matter exists in these three states. You can see in the diagram as well what each state of matter looks like. In a solid, you can see that all the atoms are very close together, they are tightly packed, and the atoms are not free to move. They are held together in a regular structure. This is in the solid state. In the liquid state, Ibrahim, you can see that the particles, they are still close together, the atoms or particles. They are close together, but they are not held in a rigid, regular structure like a solid. They are free to move around. In a solid, the particles cannot move around. In a liquid, the particles can move around. That's why water flows, but a solid doesn't flow, right? Water, it flows because it's a liquid. Any liquid flows. And in a gas, you can see that the particles are very far apart and they are obviously also free to move. So these are the structures of each state of matter. Now let's move into atoms in a bit more detail. So atoms are fundamental building blocks of matter. As I told you, everything is made up of atoms, and they combine together to make larger particles that we call molecules. Atoms, they combine together to make molecules, right? So each kind of atom is the smallest representative unit of an element. For example, gold. You're gonna have gold atoms. A gold atom is the smallest unit of gold. For example, iron. An iron atom will be the smallest unit of iron. Oxygen. An oxygen atom will be the smallest unit of oxygen. Okay? Now, atoms are made up of three particles: protons, neutrons, electrons. You probably know this already. In the nucleus, we have protons and neutrons. And around the nucleus, electrons orbit the nucleus. They move around the nucleus, right? You can see that in the diagram as well. This is the nucleus of the atom. You have protons and neutrons inside the nucleus, and around the nucleus, you have a bunch of electrons orbiting the nucleus. Hold on, sorry. You have a bunch of you have a bunch of electrons orbiting the nucleus. This is the basic structure of an atom. Okay, protons are positively charged, they have a positive charge, a plus charge. Neutrons, they do not have any charge, and electrons are negatively charged. Okay, Ibrahim? Now, always keep in mind that in an atom, the number of protons always equals the number of electrons. This is in an atom. This is in an atom. The number of protons is always equal to the number of electrons. Now, each charge of a proton is plus 1. Each charge of an electron is negative 1. Okay? That means that because the number of protons and the number of electrons in an atom is the same, the charge on the atom is neutral. The atom overall does not have any charge. Why? Let's take, for example, lithium. Lithium is an atom. It has three protons, and because in an atom the number of protons is always equal to the number of electrons, if it has three protons, then that means it also has three electrons. And each charge on the proton is plus 1. So if you have three protons, the total positive charge is going to be plus 3. Now, if you have three electrons, each charge on an electron is negative 1. So if you have three electrons, the overall negative charge is going to be minus 3. Now, what is the total charge on the entire atom? You have plus 3 positive charge from the protons, you have negative 3 negative charge from the electrons. If you add plus 3 and minus 3 together, what do you get? You get 0. That's why the charge on an atom is 0. An atom is always neutral. Now let's look into a bit more detail about what atoms actually make. What can atoms make? So, first of all, what is an element, Ibrahim? An element is the simplest form of matter that has a characteristic set of properties. What does this mean? If you look at the periodic table, Ibrahim, you know what the periodic table is, right? Search on Google periodic table. If you look at the periodic table, you will see that there are, I believe, 120 elements. If I'm not wrong, I might be wrong. Maybe there's more than that. But each box in the periodic table has a symbol like Ne, Au, C. These symbols are symbols for different elements. The periodic table has all the elements that exist in the universe. For example, gold is an element, carbon is an element, neon is an element, oxygen is an element, nitrogen is an element, lithium is an element, magnesium is an element, argon is an element. All of these are different elements, right? And each element, Ibrahim, has its own specific set of properties, right? For example, gold, iron, silver, these are all metals. These are all metallic elements. And all of these metallic elements have metallic properties. Further, each metal has its own set of different properties as well. For example, gold, it is much softer than silver, right? Silver is hard, gold is very soft. Iron, iron can rust, gold cannot rust. So these are the different properties of different elements, right? Each element has different chemical reactions, they have different properties. So each element has a unique name and a chemical symbol. Like I told you, NeAuC, these are all chemical symbols, right? Now, Ibrahim, so that is what an element is. What is a molecule? What is a molecule? A molecule is when two or more atoms combine. When two or more atoms combine, that is what we call a molecule. That particle is called a molecule, right? Now, how do the atoms combine? The atoms combine by joining together with each other through chemical bonds. Through chemical bonds. Let me give you an example, Ibrahim. Water. What is the formula of water? You probably know this. It is H2O. What does this mean? It means that in a molecule of water, you have two hydrogen atoms, you have one oxygen atoms. If I draw the structure of water, it's going to look like this. This is going to be our oxygen atom. We're going to have two hydrogen atoms like this. And this is what the bonds are going to look like. Okay? The hydrogen atoms are joined to the oxygen atom through these chemical bonds. This is what we call a water molecule. It's called a water molecule, right? So, Rahim, a molecule is made up of atoms that are combined together. We have two hydrogen atoms, one oxygen atom in a molecule of water, and they're joined together through these chemical bonds. Okay? So, this is a very simple molecule, but we have many other very complex molecules. There are many complex molecules that exist. Water is just a simple molecule. For example, a DNA molecule. You know what DNA is, right? DNA in the human body. A DNA molecule is made of billions of atoms. Billions. This water molecule is only made up of three atoms, Ibrahim. A DNA molecule is made up of billions of atoms. Okay? So let's go through a few other through a few other compounds, right? Like what is the difference between molecule and compound, Ibrahim? So a water molecule is this. I do the structure of a water molecule. When you have a bunch of molecules together, they make a compound. Water itself is a compound. The liquid that you drink, water, it's a compound, right? And in that compound, you have water molecules. So we can say, Ibrahim, that the water compound is made up of water molecules. So compounds and molecules are not the same thing, right? Uh, Another example, salt. Salt is made up of NaCl, right? So salt is also a compound. Another example, Ibrahim, carbon dioxide. What is carbon dioxide? CO2. One carbon atom like this, and you have two oxygen atoms like this that are joined together to the carbon atom through chemical bonds. This is one molecule of carbon dioxide, right? So the compound carbon dioxide is made up of carbon dioxide molecules. Let's go through some other examples of compounds as well. We have salt, common table salt, NaCl. That is a chemical formula of salt. You have one sodium atom, which is Na. The symbol for sodium is Na. You have one chloride or chlorine atom as well. What is the symbol of chlorine? Co. Right? What about sucrose? Sucrose, you might have heard in biology, it's a sugar. Okay? This is the chemical formula of sucrose. You have 12 carbon atoms, you have 22 hydrogen atoms, you have 11 oxygen atoms. Right? So this is one molecule of sucrose. Then vinegar, what is the chemical formula of vinegar? C2H3O2. So two atoms of carbon, three atoms of hydrogen, two atoms of oxygen. Baking soda, you have one atom of sodium, one atom of hydrogen, one atom of carbon, three atoms of oxygen, and they are joined together to make the molecule of baking soda. So these are some examples of compounds, right? So Ibrahim, a molecule, it can be made up of it's made up of a bunch of atoms that are joined together. This is what this means. Single atom plus single atom, when they combine together, they make a molecule. Now, Ibrahim, if a molecule is made up of the same atoms, if a molecule is made up of the same atoms, then it makes an element. And if the atoms that are joined together are different, then what is formed is a compound. Keep this in mind. Let me give you an example. Let's look at oxygen. Oxygen is an element, correct? Now, what is oxygen made up of? Oxygen is not, oxygen doesn't exist as one single oxygen atom, Ibrahim. Oxygen exists as a diatomic molecule. What is a diatomic molecule? This is what the diatomic molecule of oxygen looks like. You have two oxygen atoms that are joined together. You have two oxygen atoms that are joined together. This makes a molecule whose chemical formula is O2. O2 means two oxygen atoms that are joined together. And O2, Ibrahim, is an oxygen molecule. Can you see that this molecule is made up of atoms of the same type? Both of the atoms are oxygen. They're joined together to make the oxygen molecule. So when atoms of the same type they join together, that equals element. Because oxygen, as we know, is an element, Ibrahim. It's an element. So oxygen molecule, this is an element. This equals an element. Now, Ibrahim, if the atoms are different types, I gave you the example of water. Water is not an element, right? It's a compound. Why? Because it's made up of different types of atoms. How? Again, you have an oxygen atom in water, and then you have two hydrogen atoms. You can see that in water, you have different types of atoms. You have oxygen atoms and hydrogen atoms. They're different. And the chemical formula of water is H2O. Two hydrogen atoms, one oxygen atom. This is a water molecule. And Ibrahim, because the atoms are different and they're not the same, a water molecule equals a compound. It does not equal an element. Water is not an element. If you look at the periodic table, you will not find water on the periodic table because it is not an element. Let's move on. Now we're going to learn about the different types of energy. We have kinetic energy. So something that moves has kinetic energy. It's related to moving, right? If a ball is moving, it has kinetic energy. If a car is moving, it has kinetic energy. If you are moving right now, you have kinetic energy, right? Anything that moves has kinetic energy. So kinetic energy is related to movement, Ibrahim. Second, potential energy. What is potential energy? Potential energy is the energy that something has because of its position. Because of its position. It is also called, Ibrahim, stored energy. It is also called stored energy. So potential energy is not related to movement. It is not related to movement. It is related to an object's position. What does this mean, Ibrahim? Imagine that you are standing on the ground and you see a plane above that is flying in the sky. Now, the plane, if fuel runs out, the plane will fall down to the ground. But you, Ibrahim, because you are already on the ground, you can't fall down further into the ground, can you? You can't travel even more down. You can't fall downwards because you're already on the ground. But the plane, however, Ibrahim, if the plane runs out of fuel, it's going to fall down to the ground. It's going to crash into the ground. This is because the plane has gravitational potential energy. There's different types of potential energy, Ibrahim. Electric potential energy, gravitational potential energy, magnetic potential energy. We're talking about the plane. We're talking about gravity in this case, right? Because the plane is in the Earth's gravitational field. So, Ibrahim, because the plane is high up in the sky, it's away from the ground, it's away from the Earth. It has gravitational potential energy. As soon as the plane's fuel runs out, because of this potential energy, the plane is going to fall downwards. It's going to start falling downwards because of this potential energy. So the only thing that is keeping the plane up in the sky is the fuel, is its engine. Without the engine, without the fuel, without the thrust force, the plane would simply fall down. So Rahim, if you are on the ground, you do not have any potential energy because you're already on the ground. But the plane, because it's high in the sky, it has potential energy. It has the potential to fall down, right? And this is because of the plane's position in the Earth's gravitational field. Because the plane is further up, it's away from the Earth, that's why it has potential energy. Then Ibrahim, thermal energy. Thermal energy is related to temperature, as you know. Something that is hotter has higher thermal energy. Something that is colder has less thermal energy. But Ibrahim, if you explore this in more detail, then you will realize that thermal energy is the total kinetic energy of all the particles that make up matter. What does this mean? How is this related to temperature? You might be confused now, but let me explain. Ibrahim, if something has high temperature, if something is very hot, for example, let's look at this metal rod. In this metal rod, you have a bunch of these particles, right? You have a bunch of these metal particles. If you heat up the metal rod, Ibrahim, if you heat up the metal rod, what's going to happen? The metal rod obviously is going to become very hot. The temperature of the metal rod is going to increase. Now, what happens when the temperature increases? The particles, they begin to vibrate. They begin to move around. I mean, not move around because in a solid, particles cannot move around. They can only vibrate. So they begin to vibrate faster. And the hotter the metal rod becomes, the faster the particles vibrate. Now, Ibrahim, I told you that kinetic energy is related to movement. So if the particles are vibrating very fast, they're going to have more and more and more kinetic energy. Basically, the higher the temperature, the faster the vibrations, and the more kinetic energy each particle has. And the more kinetic energy each particle has, the more thermal energy the metal rod has. That's why the thermal energy of matter is the total kinetic energy of all the particles that make up the matter. This is how this is related to temperature. So the thermal energy of the metal rod, Ibrahim, is directly related to how fast the particles are vibrating in the metal rod, how much kinetic energy each particle has in the metal rod. The higher the temperature, the faster they move, and the higher kinetic energy they have. The lower the temperature, the slower they move, and the less kinetic energy they have, and the less thermal energy the metal rod has. So this is how we can link kinetic energy to thermal energy. Ibrahim, the same thing goes in water. In water, you have particles that are far apart. Like they're close, but they're not as close as in solids. So here, when you increase the temperature, the particles begin to move around faster. In a solid, the particles can't move around, they can only vibrate. But in liquids and solids, the particles they begin to move around faster. They start moving around, jumping around faster. And the same thing happens. When they move around faster, they have more kinetic energy. If they have more kinetic energy, they have more thermal energy. And finally, Ibrahim, chemical potential energy is a type of potential energy. I told you that potential energy is also stored energy, right? So chemical potential energy is the energy stored in the chemical bonds that hold atoms together. Ibrahim, this energy can be released or absorbed during a chemical process. This energy can be released or absorbed during a chemical process. And we're going to learn about this in more detail later on. Let's move on. Yeah. So look, chemical potential energy in firewood, Ibrahim. What is happening? You are burning wood, right? When you light up a firewood, when you light up a bonfire, you're burning wood. This is a chemical process. This is a chemical reaction, right? The compounds and the molecules inside the wood, they are burning, Ibrahim. They are burning. They are reacting with oxygen at very high temperatures, and this is what we call burning. And Ibrahim, I told you that the chemical potential energy can be released or absorbed during a chemical process. So when the molecules inside the wood, Ibrahim, they react with oxygen at high temperatures, the wood begins to burn. It produces a fire. And what is fire? Fire is the release of energy, Ibrahim. Release of energy. So when you're burning wood, in this chemical process, the chemical potential energy is released. Energy is released. Okay? Same thing in explosives, Ibrahim. Same thing. And the chemical reaction in explosives, energy, chemical potential energy is released. Do you remember that we learned about exothermic and endothermic reactions way before when I was teaching you chemistry for your previous class? We learned about exothermic and endothermic reactions. In exothermic reaction, energy is released. In endothermic reactions, energy is absorbed. Ibrahim, same thing here. This is the same thing. In exothermic reactions, chemical potential energy is released, right? In endothermic reactions, chemical potential energy is absorbed. So this is the same thing. Then this is an example of potential energy. I told you that potential energy is the energy that an object stores because of its position. If you have a ball that is high up, it has potential energy because it's away from the ground. It is higher up in the Earth's gravitational field. That's why it has potential energy. As soon as you let the ball go, because of its potential energy, it's going to fall downwards. And the potential energy gets converted into kinetic energy. The potential energy gets converted into kinetic energy because the ball starts moving as it falls down. So the potential energy is being converted into kinetic energy. Thermal energy, I already told you everything here. Yeah. So Ibrahim, interaction of matter and energy. What is the interaction between matter and energy? So look, a system is a portion of the universe that the scientist identifies for study, right? The surrounding is everything around the system. Energy can flow into a system from the surroundings. It can also flow out of a system into the surroundings. What does this mean? This is basically, Ibrahim, how scientists see the world. Let me give you an example. Let's say that you go to the chemistry lab in your school and you're doing an experiment. You're doing an experiment between two chemicals. So you put the two chemicals into this flask right here. Okay? You put the two chemicals into this flask right here. You mix them together and you observe the reaction. For you, Ibrahim, the system that you are observing, that you are studying, is this flask right here. This is your system. Everything that is around the system, including you, including your friends, including the lab, including the teacher, including the school, everything that is around the system, that is not part of the system, that is what we call surroundings. And energy, Ibrahim, can flow into the system from the surroundings, or it can flow out of the system to the surroundings. For example, if I'll give you the same example, right? You're doing this experiment, you're mixing two different chemicals in this flask right here. This is your system. If the reaction between the two chemicals, Ibrahim, is exothermic, meaning that it releases energy, that energy is then going to flow out of the system and into the surroundings. And everything is going to become hot. For example, in the example of the firewood, right? When you burn firewood, it's an exothermic reaction. So energy is released to the surroundings and everything becomes hot in the surroundings, right? If you go near the firewood or the bonfire, you will feel the warmth of the fire. Same thing here. If it's an endothermic reaction, Ibrahim, then energy is going to go from the surroundings to the system. And everything around the system is going to become cold because energy is flowing from the surroundings into the system. It's leaving the surroundings. The heat energy is leaving the surroundings. That's why everything becomes cold in an endothermic reaction. And system plus the surroundings, that equals the entire universe. So Rahim, we have different types of systems. In an open system, energy and matter can flow into the system and out of the system. As I told you in the example of the firewood, right? The heat energy can go out of the system into the surroundings. In the example of the bonfire, the firewood. This is what we call an open system. Ibrahim, in a closed system, only the energy exchanges. Only the energy can exchange between the surroundings and the system. In an open system, energy and matter can exchange. Energy and matter can leave and enter the system, right? In an open system, like you have an open flask, gases can enter the flask, gases can leave the flask. This is an open system. In a closed system, matter cannot enter or leave the system. Like gases cannot enter or leave the system, liquids cannot enter or leave the system. Only energy can be exchanged. That's it. In an isolated system, Ibrahim, matter and energy, both of them are contained. Right? Let me give you an example. So here, if you have a cup of coffee and you just leave it as it is, this is an open system. Imagine that the cup of coffee is your system. If you just leave it like that on the table, it's going to be an open system. Why? Because heat energy can flow out of the coffee and into the surroundings, right? Gases can also leave the coffee. You can see that the gas is leaving the coffee, the steam is leaving the coffee. Gases can enter the coffee. So this is an open system. In a closed system, if you put a lid on top of the coffee, gases cannot enter or exit the system. Any other matter cannot enter or exit the system. Doesn't matter if it's gases, liquids, solids, whatever. Nothing can enter or exit the system. But heat transfer is still there. Heat is still being transferred. In an isolated system, heat cannot be transferred, mass cannot be transferred either. Okay, so this is a if you keep the coffee in a flask in a thermodynamic flask, the coffee will stay hot because heat is not being transferred, and the matter is also not being transferred. Okay, Ibrahim, what is an atom? List three subatomic particles along with the charges. So Ibrahim, I'll dictate the answers. You write them down yourself. An atom is the fundamental particle, is the fundamental building block of all matter. And the three subatomic particles are protons, neutrons, and electrons. What is an element, Ibrahim? An element is the most basic unit of matter. Each element has its own specific properties. Um, okay? Don't write this exactly as I'm dictating. Write it in your own words. Give two examples. You can give any two examples from the periodic table. I want you to give your own examples. Question 3. Explain how a molecule is formed. A molecule is formed when two or more atoms combine together through a chemical bond. Okay? In a chemical process or reaction. That is how a molecule is formed. Question 4. What is the difference between an element and a compound? In an element, Ibrahim, an element is made up of the same types of atoms. A compound is made up of different types of atoms. Question 5. What is kinetic energy? Give an example. Kinetic energy is the energy that a moving object has. One example, if you play cricket, the cricket ball, because it's moving, it has a lot of kinetic energy. What is potential energy? Potential energy is the energy that an object stores because of its position. For example, gravitational potential energy. An airplane in the sky has a lot of gravitational potential energy. And if you're standing on the ground, then you will have no potential energy. Question 7. What is thermal energy? How is it related to kinetic energy? This is your hot question. You have to do this yourself. I have already given you the entire explanation before. If you want, you can even watch the recording back and rewind the recording. Question 8. What is a system in scientific study? A system, it's given here. A system is a portion of the universe that the scientist identifies for study. You should just memorize this. Okay? Just memorize this. Question 9. Explain the difference between an open, closed, and isolated system. In an open system, matter and energy can be exchanged between the system and the surroundings. In a closed system, only energy can be exchanged, matter is not exchanged. In an isolated system, matter and energy both cannot be exchanged between the system and the surroundings. Okay, so what else is there, Raheem? Okay, this is chapter 2, modeling atoms. So, Raheem, you need to know how to write down the symbols for atoms and what the numbers mean. In the periodic table, you will see that each element has two numbers, right? One number on top, another number at the bottom. So, Ibrahim, the number at the top, the whole number, that is what we call the atomic number. What is the atomic number? The atomic number tells us the number of protons inside an element, inside an atom of an element. For example, oxygen. Oxygen, let's go to the periodic table actually. I'll show you. Look. Okay. Look. Look at oxygen right here. This is oxygen, right? What number does it have on top? 8. 8 is the atomic number. That means that oxygen, an atom of oxygen, has 8 protons. How do we find the number of electrons? I told you, Ibrahim. In an atom, the number of protons equals the number of electrons. So if something has 8 protons, it's also going to have 8 electrons as well. Now, how do we find the number of neutrons? Look, how do we find the number of neutrons? You have to look at the mass number of an element. What is the mass number? The mass number of an element, Ibrahim, is the number at the bottom. Go through the periodic table. Look here. If you look at any element, you will see that you have a number on top. That is what we call the atomic number. The number at the bottom is the mass number. It is the mass number of the element. So you have to use this formula to find the number of neutrons. The number of neutrons in an atom equals the mass number minus the number of protons. Okay. So what is the mass number of oxygen? If you round it off, it's going to be 16. In the periodic table, it's going to be 15.999. You have to make it a whole number. So just round it off, okay? So 16 is the mass, protons is 8. What is 16 minus 8? It is also 8. Same thing for sodium, Ibrahim. You have the number at the top. This is the uh oh, okay. In some, Ibrahim, in some periodic tables, the number at the top is the mass number, at the bottom is the atomic number. In this periodic table, the atomic number is at the top, the mass number is at the bottom. If you don't know which one is the atomic number, which one is the mass number, the bigger number is always, Ibrahim, the bigger number is always the mass number. You can just use this rule. If you don't know which one is the atomic number or the mass number, the bigger number is always the mass number, the smaller number is always the atomic number. Then you can use the formula to find out the number of neutrons. Okay, so I already explained this. Now, Ibrahim, what about an isotope? What is an isotope? Isotopes are atoms of the same element that have the same number of protons but a different number of neutrons. Look, Ibrahim, what makes an element, right, is the number of protons. The atomic number of an atom defines which element it is. For example, hydrogen. Hydrogen is always going to have one proton. It's always going to have one proton, hydrogen. You can see that in the periodic table. The atomic number of hydrogen is 1. Look, it's 1. What about helium? This is helium. The atomic number of helium is 2. Helium is always going to have 2 protons. Lithium is always going to have 3 protons. Oxygen is always going to have 8 protons. So the number of protons defines what an element is. So the number of protons of an element never changes. Oxygen can never have 7 protons or 6 protons or 9 protons. It's always going to have 8 protons. Rabihim, what can change? The number of neutrons can change. The number of neutrons do not define the element. So hydrogen can have 1 neutron also. It can have no neutrons. It can also have 3 neutrons. So this version of hydrogen is the hydrogen without any neutrons, only a proton. This version of hydrogen has 1 neutron. This version of hydrogen has 2 neutrons. All of these are isotopes of hydrogen. They're isotopes of the same element. All of these are hydrogen atoms, okay? You also have carbon isotopes as well, carbon 12 and carbon 14, okay? So in one isotope of carbon, the mass number is 12. We call this the mass number is 12. Because carbon has 6 protons, in carbon 12, 12 minus 6 is 6. So it's going to have 6 neutrons. Carbon 14, the mass number is 14. So how many neutrons are going to be there in carbon 14? Because carbon always has 6 protons, since that is the atomic number, the number of neutrons is going to be 14 minus 6, which is 8 neutrons. So there are 2 versions of carbon, one with 6 neutrons, one with 8 neutrons. Okay? How do we estimate the mass of an atom? We simply add the number of protons and neutrons together. That is how we get the estimated mass of an atom, Ibrahim. We estimate that one proton has a mass of 1, one neutron has a mass of 1. So when you add the number of protons and neutrons together, you will get the mass number of the atom. Why don't we include the mass of electrons inside this calculation? Because electrons are so small, so tiny, that their mass is negligible. So we don't include them. That's why. So, Ibrahim, what is the element that we use to measure the atomic mass? Carbon 12. You should memorize this. Why do we choose this element? Because carbon 12 is stable, common, and easy to measure. Just memorize these answers, okay? Just memorize them. Average atomic mass, okay. Finally, we have some calculations, okay? I'll teach you how to do these. So, Ibrahim, what is the meaning of atomic mass unit 1 AMU? Like, look, Ibrahim, You know how we use kgs, kilograms, grams, milligrams, and stuff? These are the units of mass. Now we also have units for atoms as well. We have units of mass for atoms as well. The reason why we don't use kilograms or grams with atoms is because atoms are so small that if we use grams or kilograms, the number is going to be very small. It's going to be difficult to deal with. That is why for atoms, we have its own unit of mass. What is a unit called? It is called atomic mass unit. One atomic mass unit is equal to 1/12, meaning 1 over 12 of the mass of a carbon 12 atom. You should just memorize this. You don't need to know what it means exactly, just memorize this. Now, what does this mean? This means that one proton has a mass of 1 AMU. One neutron has a mass of 1 AMU. Okay? That's why I told you the mass of one proton is 1, mass of one neutron is 1. So if you add the number of protons and neutrons together, you get the mass number. So this is what we call the atomic mass unit, Ibrahim. It's the mass unit we use for atoms. Now, isotope abundance. Ibrahim, I told you that isotopes are different versions of the same element, right? With different number of neutrons. If you have a sample of an element like carbon, in that sample, you're going to have carbon 12 and carbon 14. Both of these are the same, both of these are different versions of the same element. Carbon 12, carbon 14, both of them are carbon. Okay? So you're gonna have both of these versions inside that sample of carbon. Like if you have 6 grams of carbon inside that sample, you're gonna have both of these versions. Now, which one is more abundant? For carbon, carbon 12 is more abundant. You don't need to memorize this. I'm just telling you. Carbon 12 is much more common than carbon 14. Carbon 14 is rare. Carbon 12 is much more abundant. What if you have a sample of chlorine, Ibrahim? Chlorine has two isotopes, two versions. Chlorine 35 and chlorine 37. In chlorine 35, the mass number is 35. In chlorine 37, the mass number is 37. Okay? In a sample of chlorine, which one is more abundant? Chlorine 35. It is much more common. Approximately 75% of all chlorine samples, they are chlorine 35. Okay? And 25%, the rest are chlorine 37. This is what we call isotope abundance. Now, if you have all of these different isotopes, how do you find the average mass? Because in the sample of chlorine, you have two different isotopes, right? 35, 37. Both of these isotopes have different masses. So you need to get the average. How do you get the average? How do you get the average atomic mass of an atom? This is the formula. Mass number of isotope 1 multiplied with the percentage abundance plus mass number of isotope 2 multiplied with the percentage abundance divided by 100. This is equal to the average atomic mass. For example, let's find out the average atomic mass of chlorine, of the sample of chlorine. How about we do that? So in the sample of chlorine, chlorine 35 has 75% abundance. So you will do 35 multiplied with 75. Okay? Plus, what is the mass number of isotope 2? It's 37. So you'll do 37 multiplied with 25. And then divide with 100, and you will get the average atomic mass of chlorine. Another example. What is the average atomic mass of oxygen? If its abundance in nature is 99.76% oxygen 16, 0.04% oxygen 17, and 0.20% oxygen 18. So same thing, 16 into 99.76 plus 17 into 0.04 plus 18 into 0.2. Divide by 100, you will get the answer, 16 AMU. Okay, Ibrahim, you have these questions left. These are going to be your practice questions. I don't want to do every single question with you because you also need to practice, especially for the calculation questions. So please do these yourself. I will check the answers. If you got anything wrong or if you have any doubts, I will correct you. I will clear up your doubts. So please contact me on WhatsApp. Okay? Assalamu alaikum. Bye bye. Good luck for the exam tomorrow.